every interval that we've looked at so far has been segmented evenly. So we've had the step size h, and h has been consistent. But not all the time do we get problems or scenarios to where we have equal segments. And so what we're going to do is we're going to look at a really easy way to be able to perform integration with unequal segments. Now, if we wanted to do it by hand, which we certainly could, we could just utilize the idea of the trapezoidal rule. And what that would do is that would take the distance between x0 and x1, and we could call that h1, and we would just take the height, so the first height plus the second height, so this should be an f here, and this should be an f here, and this should be an f here. Okay. And we would just divide that by 2, and we would just add them all up. And that's a pretty crude but effective way to be able to approximate the integral for unequal segments. Now, a really nice way to do it is to just use Matlab and use this function trapz. And if x and y are numerical row vectors, then we can easily produce some sort of integral for those values. And what it does is it just literally goes through and uses the trapezoidal rule to be able to find what the integral is numerically. All right, so let's take a look at an example as where we might use this. All right, so one thing we could do is we could say that the total mass for a variable density rod, all right, is given by mass is equal to 0 to L P of x, A of x dx, where M is the mass, X is the distance along the rod. And remember, it's variable density. P is that density, so that the density differs depending upon how many meters we are away. X is the distance along the rod, and the density is P, and A is going to be the cross-sectional area. All right, so density times area is going to give us what that mass is going to be. And we just want to find the mass for a 20-meter rod. All right, so we're going to evaluate this. So what we need to do is we need to first store all of these into row vectors, then multiply P and A, and then integrate it by using this trapz function. All right, so I'm going to bring up Matlab, and I'm just going to pull this off to the side so I can type in these row vectors. All right, so let's have our x. And again, notice that x is not equal with respect to the segments. All right, so we have 0 and 4 and 6, which are certainly not equal, at least arithmetically or linearly. And then we have 8, 12, 16, 20. All right, so we have an interval of 2 and an interval of 2 and an interval of 4. So that's what we mean by unequal segments. The pressure, or I'm sorry, the density at each point, that's going to be 4, 3.95, and then 3.89, 3.80, 3.60, 3.41, and 3.30. And then finally, the cross-sectional area, which I'm going to call A, is going to be equal to our 100, 103, 106, 110, 120, 133, and 150. All right. Now, I'm going to create another row vector, which I'm going to call PA. And PA is going to be equal to, now be careful with this, P dot times A, right? Because we want to make sure that it's going to be elemental multiplication as opposed to matrix multiplication, right? If we try it without the dot, it's not going to work for us. All right. And then finally, all we're going to do is we're going to find the mass. So the mass is going to be equal to that trapz function. So we're going to say trapz x. All right, so these are the intervals. All right, so what it's going to do is it's going to find the interval from 0 to 4, 0 to 6, etc. And then also, we're going to compare that with PA. All right, so we have our new matrix or new row vector that we just made, PA. All right, and remember what we're trying to do. We are trying to evaluate this interval, right? Fortunately, x goes from 0 to 20, so we don't actually have to change x. However, if this were different, so if the upper bound were not 20, then we would have to change that. All right, but fortunately, we don't have to change it. And we're going to do an f print f. So this is a really quick problem. So f print f, and we're going to say the mass of the rod, or we can say the mass of the 20-meter rod is %F, and it's in grams. All right, and we're going to backslash n. All right, so let's run it, give it a try, see what happens. And we have to obviously put in mass. Might have been obvious to everybody else but me, apparently. All right, and we get that the mass of the 20-meter rod is 863.35000. All right, so a really easy example of how we can go through and numerically find our integration just by using this trap z function, right? And that's not the only one that exists for these types of problems, all right? So just really quickly, if you want to see another one, and I haven't tried this one, so if it doesn't work, I apologize. But I believe that there's, instead of trap z, there's like cumulative trap z. So it's a cumulative integral. So we could say trap z. All right. And what it'll do is it'll show you the integral along each part. All right. So that's pretty cool. But since we only asked for, and by the way, this is a row vector, trap, or traps. So, but really all we want is this. All right. So if you want to see what the integral is along each stage, so between 0, 4 and 4 to 3.95, then sure, you could go ahead and, or actually it would be the product of these two. So it would be 0 and 400, and then 4 and 3.95 times 103. So that's where these values are all coming from, and we just add them up each time. So this is the sum and the sum and the sum and the sum and the sum. So that's pretty cool that we can look at it that way, but I don't necessarily know for this problem how useful it is. I mean, we could see what the mass is as we go up each segment. So for instance, if we ran this again with traps, then we could say that, okay, well, initially the mass is 0, which makes sense because we haven't gone anywhere along. All right, so we just have right here. But then over time, we start getting more and more mass as we go further along the length of the 20-meter rod. All right, so hopefully that gives you a good overview of our numerical integration, both for equal segments, by utilizing the Newton-Cote method, by utilizing some of the older methods that we've seen in integral calculus, and then also these numerical functions, the traps and the traps functions.